10-4 is going into probability of disjoint or overlapping events. So in our previous section, we had our with and events, or we had our independent and dependent events. And basically, when that happened, we had two formulas that we had to look out for. We had our independent formula, which was the probability of A and B. Okay, so drawing a heart and a heart. And if we put those cards back once we were done, well then the first event did not affect the second event, and so therefore we just multiplied. Then it came to our dependent events, and that was when we had the same scenario. We had needed to draw two cards, but we did not replace our card back once we were done. So this was still the probability of A and B, a heart and a heart, but it was the probability of drawing a heart the first time and probability of drawing a heart the second time, given that we already took a card, or given that event A already occurred. So that is what 10-3 was about. Now 10-4 is going into the next piece of it, which is when we are looking for or statements. Okay, so this will be with or events. You have two outcomes. You can either have overlapping or disjoint. Overlapping or disjoint. And there's two pictures over here. When you have overlapping materials, obviously this is going to have some numbers in common or have some items in common. For example, if I was looking for multiples of 2, then that would be 2, 4, 6, 8. If I were looking for multiples of 4, well, that would be 4 and 8. And so we would have overlapping numbers in those particular cases. And so the formula for this section, for at least overlapping, I should say, let me erase this, is going to be the probability of A or B is going to equal probability of A plus probability of B minus the probability of A and B. Okay, and so let me explain that for a second. Basically what's happening is we have our probability of A over here, as you can see. So I've included all of my pieces inside of my A event. But then if I want to include B, all right, I include this piece, but I notice how I'm including the middle section, that intersection, twice. And so to avoid having extra information, I need to subtract one time so that I'm not counting the middle twice. Okay, so that's the reason why we're subtracting the probability of A and B. And then if we were to have disjoint information, that would be this type of picture. As we can see, there is no intersection, and we call this mutually exclusive. These do not have any events in common or any numbers in common. So before you start, you should always ask yourself, is this going to be overlapping, or does it have overlapping information, or is it mutually exclusive? And the formula for this is going to be probability of A or B, and it'll still be a probability of A plus the probability of B, but because there is no intersection, I do not need to subtract anything else, and this would be my final piece in my formula. So let's go ahead and do an example with the formulas now. Example 1.1 and 1.2 say find the probability, and so we're going to be given a standard 52 card deck, and I just found this out because I was taking the quiz in preparation to help you guys for help class, and I noticed that the book does not include ace as a face card. Alright, so ace is not a face card, just so you guys are aware. So please make sure that when you are doing this, you are not considering ace a face card. So that means instead of there being 4 face cards in each suit, there's actually 3. So there's only 12 total face cards, according to this textbook. It really depends on the book, so just make sure you figure out, what that is. Anyway, so we are looking at this, and we're looking for the probability that it is a 10 or a face card. And we have to ask ourselves, is this disjoint or is it overlapping? And we can see that it is not possible for a 10 to be a face card or for a face card to be a 10. It's not possible. So there are no common cards or common things between these two. And so we would say these are mutually exclusive or disjoint. This is disjoint. So I can write my formula to say the probability of getting a 10 or face card is equal to the probability of 10 plus the probability of F. And I don't have to include any minus because I don't have any intersecting parts. So the probability of getting a 10 is a 4 out of 52. That's 1 10 in each suit, and there's 4 suits, plus the probability of getting a face card, well, that's going to be 12 out of 52. Add that together to get 16 out of 52. We can reduce that to be 4 out of 13, or approximately 30.8%. And that is our answer. Okay, letter B says, given a standard 52 card deck, what is the chance of a face card or a spade? So the question is, can a face card be a spade? And the answer is yes. So because that is true, we know we have intersecting parts, or it is going to be overlapping. So my formula should say the probability of a face card or spade is equivalent to the probability of a face card plus the probability of a spade minus the intersecting parts, or a face card and a spade. All right, so now I just need to figure out the probability of each piece. The probability of a face card, well, I already know that's going to be a 12 out of 52, plus the probability of a spade. Well, there's only 13 spades out of the whole deck, and then minus the probability of a face card and a spade. Well, there's 3 face cards in the spade suit, so that'll be minus 3 over 52. If I add this across, it's going to give me a 22 out of 52, reduced to get 11 over 26, which is approximately 42.3%. And this is our answer. Example 1.2a says, given two 6-sided dice are rolled, what is the probability that the sum of the numbers rolled is a multiple of 4 or is 5? Okay, so that the second piece, or is 5, that means or equals 5. So we can actually go to 10-2, or is it 10-2? No, it's actually 10-1, where it talks about the complement of an event. And in those notes, I gave a picture of all the combinations you could have possibly gotten for multiplying, or for rolling 2 dice, and what the sum of it would be. So I'm going to just show that picture to you really fast, and then we'll continue on with this problem. So here is that picture that I mentioned before, and we are going to be using this in our sort of, if you have it off to the side or have a printout of it, just make sure you have it when you're doing this problem, because I'm just showing you what it looks like so that we remember where it came from, but I'm not going to actually show it as I am working on the problem. So I have to ask myself, is multiples of 4 going to have any intersecting parts with it equaling 5? And the answer is no. So this is actually going to be disjoint data. I can either have 4, 8, or 12, or I can have 5, and they're not the same. So 4, 8, or 12, I have 9 out of 36 options, and then I can add that to 4 out of 36. Remember, because there's 36 possibilities, I could either be rolling a 1 and a 4, or 4 and a 1. Okay, so that's 2 combinations, a 2 and a 3, or 3 and a 2. So those are how we're getting our 5, because 2, 3, 3, 2, that's 2 combinations, 1, 4, 4, 1. Oh, 2 plus 2 is 4. Okay, so now I can add those across. I can get 13 over 36, which can't be reduced, so it's going to be approximately 36.1%, and that's our answer. Letter B, you have cards numbered 1 through 20. What is the chance your card is a multiple of 3 or a multiple of 4? And so I can think of one number that is both a multiple of 3 and a multiple of 4. And so I know that this is going to be overlapping data. So for a multiple of 3, I have 3, 6, 9, 12, 15, or 18. And remember, it only goes up to 20, so I can't go any higher. The multiples of 4 are going to be 4, 8, 12, 16, and 20. So when I start writing my formula, I have 6 out of 20 multiples of 3. Add that to my 5 out of 20. And then I have only one number that is the same in each group. And so I'm going to subtract 1 over 20. This should give me a 10 out of 20, which is the same thing as 1/2 or 50%. Okay, so again, we are just using our formulas for or statements. And please make sure you have like a card off to the side so that when you see the word and, you know you need to be multiplying. When you see the word or, you need to be adding or subtracting, depending on which formula you're using. So examples 1.1 and 1.2c are still using the formula, but it's going to be using the formula in a slightly different way. It says in 1.1c, out of 200 students in a senior class, 113 are either varsity athletes or on the honor roll. So it actually gives us our or information right off the bat. Let's keep going. There are 74 senior varsity athletes and 51 seniors on honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? So now we're looking for and information. And even though I do have formulas that can help me find my and information, they start off with giving me my or information. So I'm gonna write the or formula, probability of varsity or honor roll, that equals varsity plus honor roll minus varsity and honor roll. So now I see that I can find my and information by using this formula. So I'm just going to plug in the pieces that I have. So I see that my or statement is attached to 113, and it's out of, remember, when you're doing probability has to be between 0 and 1. So I can't plug in 113, but I can plug in 113 over the total number of students, which is actually 200. Okay, so that's going to equal, and then I have 74 senior varsity athletes, so I'll say 74 out of 200, and then I have 51 honor roll kids, so I'll put that out of 200. And of course, I still don't know the probability of the and statement, so I'm just going to copy that down. Now I'm going to combine my like terms. All right, so 74 plus 51 is 125. I'm just copying everything down. All right, and then if I subtract that, I'm going to end up with a negative 12 over 200, and that equals my negative probability of varsity and honor roll. So obviously I can get rid of both of these negatives by multiplying each side by -1. So then I'll end up with a probability of varsity and honor roll is going to equal 3 over 50. That's what 12 over 200 reduces to, which is the same thing as 0.06 or 6%, and that's my answer. So the same idea is applied to the other letter C on the right-hand side. It says out of 45 customers at a breakfast cafe, 42 customers bought either coffee or orange juice. So again, we're given our or information. There are 30 customers who bought orange juice and 40 customers who bought coffee. What is the probability that a randomly selected customer bought both coffee and orange juice? Okay, so same idea. We're going to use our formula. Probability of coffee or orange juice is equal to the coffee plus orange juice minus coffee and orange juice. Okay, so that is our first piece. Then we plug in the pieces we know. We have 42 customers bought either coffee or orange juice, so that'd be 42 out of 45. Equals, and then we have 30 who bought orange juice, so that's going to be 30 out of 45, and then we have 40 who bought coffee, so 40 over 45. Carry down our variable, if you will, and let's combine like terms. 40 plus 30 is going to be 70, so I'll copy down this side, and then this side changes to 70 over 45. Carry this variable down. If I subtract, I'll end up with negative 28 over 45 is equal to my negative probability, multiply both sides by -1, and we have our probability is equal to 28 over 45, or 62.2%. Example 2.1 says the ADA estimates that 8.3% of people in the U.S. have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for the people who don't have it. The medical lab gives the test to a randomly selected person. What is the probability that the diagnosis is correct? So with this one, I'm actually going to create a diagram or a tree diagram just so that I can sort of keep my information organized. So I'm starting off with just U.S. citizens in general. Okay, they are saying at the very beginning 8.3% of people in the U.S. have diabetes. So I'll say there are people who have diabetes. Okay, and we'll say that this is event A. And there are people who don't have diabetes. Diabetes. All right, and this would be the complement of A, which we learned from 10-1. Okay, so I'm just going to say that I have two options for my U.S. citizens. And on those options, I'm going to put my percentage, which actually I'm not going to put my percentage, I'm going to put the decimal probability. So I would take my decimal and I would move over 2 times. And so I should end up with people who do have diabetes would be 0.083. I'm just going to highlight that. Okay. So if I wanted to, I could figure out the percentage of people who don't have diabetes. Remember, the complement is just 1 minus our probability, right? So 1 minus 0.083 is going to be equal to 0.917. Okay? So let's just focus on the people who do have diabetes. They take this test, and the test can either be accurate or it can be incorrect or inaccurate. Okay? They say that the people who do have diabetes, it is 98% accurate. So by that arrow that is pointing to accurate, I'm going to say, well, this is 0.98 of a chance of being accurate. So if I were to find the complement, that would be 0.02. Okay, and then finally, the people who do not have diabetes, they say it is 95% for people who do not have the disease. So it can either be accurate, or it can be inaccurate. It can be wrong. All right, but the percentage of it being accurate for people who don't have diabetes is 0.95, and therefore the complement of that is 0.05. Okay, so all I've done is I've just created this sort of tree diagram. And so I'm going to actually use the area off to the side here, so we're just going to cross that out for a second. And I'm going to figure out, well, what is the probability that the diagnosis is correct? Well, the issue is that I have accurate or correct information on both sides. All right, it's on both sides, which is a little annoying, but it's still possible to find. So what I would have to do is I would have to say, okay, well, the probability is going to be accurate for, or actually I'll say correct, and the person has diabetes, so we'll say and A, or it is still correct and the person does not have diabetes. So now I have both an and statement and an or statement inside of my probability. And so it looks a little bit more complicated, but I promise you it's not. We are going to turn the or sign into a plus sign, and then our and signs into multiplication symbols. So really this is the probability of being correct given that event A has happened, or times the probability of the person having diabetes. All right, and then over here we'll say the probability of the test being correct or accurate given that the person does not have diabetes times the probability of that person not having diabetes. And now I can plug in all of the pieces that I need. So I'm going to go ahead and change my color so we can see that a little bit better. So the probability of it being correct or accurate given that the person has diabetes is going to be 0.98. And then the probability of this person having diabetes in the first place, according to my information, is 0.083, plus the probability of being correct, given that I don't have diabetes, would be 0.95, times the probability of not having this disease is 0.917. Okay, so now I can go ahead and multiply each side, because I'm following PEMDAS at this point. This left-hand side is going to be 0.08134. I'll round at the end. And my right-hand side will be 0.87115. If I add that up, it's going to give me 0.95249. Whew, that's a lot. So I'm going to go ahead and round it to 3, so this will end up canceling, or just going away because I'm rounding. And so it'll be approximately 95.2%. So the question was, what is the probability that a diagnosis is correct? Well, the probability of a diagnosis being correct is 95.2% of it being correct. Okay, so this is our final answer. So example 2.2 says a high school basketball team leads at halftime in 60% of the games of a season. So actually I'm going to start creating the tree as we do this. So we have our basketball team. Okay, and they're saying that they lead at the halftime, so we'll say leads at halftime, and this is our event A. Either they're leading or they are not leading at halftime. This will be the complement of A. And they're saying that out of these two options, leading is possible 60% of the time, or 0.6. So that means not leading is possible is 0.4% of the time, or 0.4 chance, I guess. And then it says after that the team wins 80% of the time. The team wins 80% of the time when they have the lead. So out of leading, there's only two options after that. They can either win the game or they can lose the game. And they're saying they win the game 0.8 or 80% of the time, and therefore the complement of that would be 0.2. And then even if they were behind and they were not leading, they still have two options. They're either going to win or they're going to lose. And they say only 10% of the time do they win if they are not leading. So this is going to be 0.1, and that means the complement of that is 0.9. Okay, so I've created my tree, and now I can go ahead and get started. The question is asking, what is the probability that the team wins a game during the season? Okay, well, again, they can either be winning over here when they lead in the halftime, or they can win when they're not leading in the halftime. And so we're going to create our formula, the probability of event A and winning, or the probability of the complement of A and still winning. Again, A just represents them leading. A bar, or the complement of A, is when they are not leading at halftime. So our probability, we can go ahead and say this is the probability of event A happening times the probability that they won, given that they were leading in the halftime, plus the probability of the complement of A times the probability of them winning given that they were not leading at the halftime. Okay, so we just expanded this a whole lot. Remember, the or turns into a plus sign here, and the ands turn into multiplication. So our probability of event A happening is 0.6, and the probability of, and I'm actually going to sort of separate this a little bit more, the probability of A bar happening, or them not leading at the halftime, is 0.4%, or 40%, sorry. The probability of them winning given that they were leading at the halftime, they said, is 0.8, and the probability of them winning given that they were not leading at the halftime is 0.1. Okay, so basically all I'm doing is I'm taking these numbers that I'm looking for here, okay? I'm taking the top one and then multiplying it by the bottom, top one, multiplying by the bottom, and then I'm adding my information together. So this is going to end up with 0.48 plus 0.04, which is 0.52, or 52%. And this is our answer. I hope that was helpful. Please make sure you are asking me questions on Teams or portals, and have a great week.